Here we go. Last class we talked more about making buffers. And like, what's a buffer? And the big takeaways are that we've got a weak acid or base and the conjugate base or acid, depending on what we have. So it's a weak something and its conjugate, meaning we've got both sides of the equilibrium expression for the weak whatever we have. So for example, if we've got acetic acid HC2H3O2, that is going to be in equilibrium with acetate. If we have significant amounts of both of those, then we have a buffer. And by significant, what we mean there is similar amounts. So if we just put acetic acid into water, it will dissociate a little bit, but it's got a Ka of like 10 to the minus 5 or something. So we won't have a significant amount of this, the products. It'll be like maybe 10 to the minus 10 molar. At the very most, it could be 10 to the minus 5 molar, and that's basically nothing. So we have to have significant and similar amounts of both of those. And that lets us neutralize from both sides. So if we add more hydroxide, that's going to use up some of our acid and turn it into the conjugate base. If we add some acid, that's going to add to the conjugate base and revert that into the acid. And that's what this slide was talking about. And our pH changes the way that we would expect it to change, just not as much as we'd expect it to change. So here's what we can do. On the middle here, we've got our initial buffer. We have equal concentrations, so significant amounts, of both our weak acid, represented by HA, and the conjugate base, which is just A-. And we can see in our solution down here, we've got 4 of each. We've got equal amounts of our weak acid and our conjugate base. They don't have to be equal. They can be different. It'll still be a buffer, but this is our best case for a buffer. If we add a little bit of acid, that's going to convert one of our acetates, one of our weak acids, whatever it is, back in, or the weak. It's going to convert one of our conjugate bases into the weak acid. So we plopped a proton on here. So that's from the conjugate base plus an H plus from the addition of this strong acid, or whatever H plus we're adding in there. The opposite is also true. We can add in a hydroxide, and that's going to pluck off the hydrogen from one of our weak acids and turn it into base. And in the process, we also make an H2O. So after we add our base, we've got a little bit more conjugate acid than we have, or conjugate base than we have the weak acid. Little changes, just a visual representation of how things are moving. All right, looking at that figure again, which of the images over here on the left, A, B, or C, best represents the amount of hydroxide added in part B? So when we're adding the hydroxide, how much hydroxide did we add? Did we add 1 unit, 2 units, or 3 units? Looking at our bits down here. Yeah, it's A. We added 1 equivalent because we only lost one of our weak acids. We've got a difference of 2 now, but that's because they're related to each other. So when one goes down, the other goes up. So one went down by 1 unit, the other went up by 1 unit, and so that now they have a difference of 2 units. All right, other fun stuff we can do. We can calculate pH change. So we've got a 1 liter buffer solution. We're told an amount of moles of our acetic acid, our weak acid. Another way that we know this is a weak acid is because we're given a Ka value. And it's small, right? It's not a big infinite Ka value or whatever. So that tells us that it's a weak acid. And then we've got NaC2H3O2, sodium acetate. And the C2H3O2 is the conjugate base of our acetic acid. We're also told additional information. Because the initial concentrations are equal, pH equals pKa equals 4.74. Calculate the new pH after adding 0.015 moles of sodium hydroxide. We learned how to do this last class. We have to do 2 tables for doing the equilibrium approach. So the first table that we're doing is just stoichiometry. We're going to do stoichiometry first. Or stoichiometry or change or however you want to think of it. This is not an ice table. So when we're starting this problem, we've got our acid, we've got our conjugate base. Our acid and our conjugate base. And we've also got sodium hydroxide that we're adding in. That's the NaOH. When we add the sodium hydroxide, is it going to react with the weak acid or the conjugate base? Does OH minus react with HA or A minus? Hydroxide is an acid or a base? It's a base. Do bases react with other bases, or do they react with acids? Acids. So it's going to react with our HA. So we're going to have our hydroxide reacting with our HA to form more A minus. So our initial amounts, 0.100, 0.100 for both of our weak acid and our conjugate base, and we're adding in 0.015 moles of our hydroxide. So we're going to use up all of our hydroxide reacting that with the HA. So our 0.1 minus 0.015 minus 0.015. And then on the other side, we're making the A minus, and so we're going to get plus 0.015 as how things change. That's going to result in our hydroxide dropping to 0. Our HA is going to drop to 0.085, and we're gaining 0.015 of our conjugate base. So it's 0.115. Now there's two ways we can go about doing this problem from here. We can either do an ice table, or since we have a buffer, we have significant amounts of both the acid and the base, and we've got a really small Ka value, a relatively small Ka value. There's another tool that we can use instead. Who remembers what that is? Yeah, the Henderson-Hasselbalch equation. So we've got pH equals pKa plus log concentration of A minus over the concentration of HA. And there's one assumption that needs to be true for us to be able to approximately accurately use the Henderson-Hasselbalch equation. X is small. X is small must be true for this to work. And we're going to estimate that, yes, it is small. That's something that we could check if we really wanted to, but I don't really want to, so I'm not going to. So now we can use our pH, or our pKa value from earlier. So our new pH is 4.74 plus log of 0.115 over 0.085. Into the calculator, get 4.87 for our new pH. Does it make sense? Does it seem like that could be the real value? Yeah, it seems like that could be the real value. We know that we're in a buffer situation. Buffers reduce the amount that our pH changes, so we're not expecting to see a big pH change. And this would definitely be a small pH change. It also increased the pH. We added hydroxide, sodium hydroxide, which is a base, which would have a higher pH. So we expect to see our pH go up. So this seems pretty reasonable. If it went up to like 10, okay, we probably did something wrong. Questions about doing that thing?
If we assumed our x was small and turns out it wasn't, would our answer be real?
I think you probably wouldn't be able to tell if x was not small based on your Henderson-Hasselbalch equation output. This also wouldn't work if we completely used up our HA or A minus. It wouldn't work out nicely because we'd be putting a 0 on the top or on the bottom. So we'd have either 0 or infinite, and that's going to return error values. But if you really want to check that x is small, you can try the x is small approximation from an ice table. Shouldn't take too long. And then you'll probably come up with something that looks okay based on that. We used it there because it's Ka of 10 to the minus 5, and we are in 10 to the minus 1 sort of territory for our concentrations. The other way that you can make a buffer situation or a buffer solution is with the weak base and its conjugate acid. The calculations are similar, but remember that Henderson-Hasselbalch is pH equals pKa plus log A minus over HA. So when we're doing it with a base, we are going to be given pKb or Kb. And we'll need to turn that into Ka or Kb. Sorry, pKb or Kb. Depending on which one of those we're given. And I wrote the wrong things and probably said the wrong things too. Those should have A's there. And a helpful tool for that, if you've got the pKa or the pKb, we can use this. Add them up, they should equal 14. If you've got Ka or Kb, you can turn them into pKa and pKb, or you can just, if you multiply them, I think that gives you 10 to the minus 14. Something like that. It's the same thing, just one of them is logged, the other's not. All right, so now we're showing, we saw a similar image to this last class, but this time we're doing it with a weak base. We've got ammonia, and we are also adding in a conjugate acid, ammonium chloride. So our weak base, to get to the conjugate acid, we picked up an H+. So we're adding both of these into our buffer solution, just showing we're making an actual buffer solution. We're adding both components. Again, we can't just add one. It wouldn't work as a buffer. All right, one for you to try. Calculate the pH of a buffer solution that is 0.50 molar in ammonia and 0.20 molar in ammonium chloride when 0.010 moles of solid sodium hydroxide is added, and you're given a pKb. All right, after a short pause, we're coming back, and anyone have a guess for our pH? Guessers? We've got a guess for 8.8. Other guessers? All right, let's find out. So we are now doing the conjugate base, or the base, weak base, conjugate acid version of buffers. This is our slightly more difficult version of buffers. So we've got some initial concentrations given to us. We need to figure out what to do with those. And we're told that we're adding a little bit of solid sodium hydroxide, and we're also told that the pKb is 4.75. What I did to start the problem is I took the pKb and turned that immediately into pKa. pKb plus pKa equals 14. So our pKa is 14 minus 4.75, which was, I don't trust my brain today, 9.25. So our pKa is 9.25, and we can start the problem. So now it's going to run pretty much the same as our other buffer examples. So we're going to start with our table that's not a nice table, but looks kind of like a nice table. And if we're really neat and tidy, it will be a nice table. So we've got our NH3, we've got our ammonium chloride. In solution, NH3 is going to be in equilibrium. It can pick up an H+, and that'll turn it into ammonium. If we were to label this like it's an acid, which of those three species, the H+, the NH3, the NH4+, is going to be our weak acid? If we label it like it's a weak acid buffer. Is going to be our weak acid. NH4+ is going to be our weak acid. This would be our HA. And NH3 would be our A-. I'm mentioning this because those are two of the numbers that we're going to be putting into our Henderson-Hasselbalch equation. All right, so we have our NH3. That's the first thing that comes up. We've got our NH4Cl, and we've got hydroxide, making our first table. We have initial concentrations of 0.50, 0.20, and 0.010 approximately. I'm not putting units on there. We can express it as molar, or we can express it as moles, since we have 1 liter of the solution. So since we have 1 liter of solution, molarity equals moles. So we're sort of working in, I guess we're working in moles in the table, but it would be pretty similar to working in molarity. All right, and then we have our change. The hydroxide is going to react with which of the other two species? The NH4Cl. So if we want to write some signs to let us know how things are reacting, that's how they're reacting. So we're going to use up our hydroxide, reacting it with our ammonium chloride, and that's going to produce some of our NH3. So we get those change values. And then our final values are going to be 0.51, 0.19, and 0. Wait. Oh no, I was looking at when I did it wrong. Cool. Okay. Henderson-Hasselbalch time. we're doing the Henderson-Hasselbalch equation. pH equals pKa. We learned earlier that that's 9.25. And we're adding to that the log of A minus base over HA acid. Oh no, my hat. Okay, 5's got its hat again. What number are we putting in for A minus? A minus is a base. And in our table, NH3 is the base, so we're going to put the 0.51 on top. That means we're putting the 0.19 on the bottom. And you should get a value of 9.68. So thank you for guessing. Didn't quite get it this time. Questions about that? So the step that we added that makes this a little bit more challenging is we had to calculate our pKa. There is a shadow Henderson-Hasselbalch equation or a dark Henderson-Hasselbalch that you can do where you calculate pOH instead. So we could do that. If you want to know how that works, you can ask me later because I think it'll just confuse you if I tell you. So let's just do the normal one instead of calculating for pOH. All right, more about our buffers. The relative amounts of buffer, of acid and base, rather, influences the effectiveness of the buffer. And we've got this big bolded box, or big bolded bullet that I'm going to box in. A buffer is most effective when the concentration of acid and conjugate base are equal. When equal, we have maximum buffering capability. Because we have a lot of both, we've got the same amount of both, so we can buffer both directions equally. So if we add in an amount of acid, we can buffer that out. If we add in an amount of base, as long as it's below our concentrations, we can also buffer that out without our pH going crazy. And to look at this, we're going to compare some 1-liter solutions of a generic buffer. We'll say that it's got a pKa of 5. And we'll calculate the percent change in pH when we add a little bit of sodium hydroxide to each. So for solution 1, we've got equal amounts of acid and conjugate base. In case I haven't pointed it out before, this little leg connecting the bottom and the side makes that an and instead of a plus. So that's plus, and this top one is and. It's not necessarily relevant, I just don't know if I've mentioned that before. in our solution 2, we have different amounts of acid and conjugate base. So let's calculate our initial pHs. Oh no, they're already calculated for us. Love that. Good prep work. So our initial pH in our first case is 5. Our initial pH in the second one is 4.05. And we've got our change tables already done for us. So we've got our amount of conjugate base and acid. So we're already in a place where we can plug in for our Henderson-Hasselbalch equation. Keeping in mind that pKa is 5. So we've got pH equals 5 plus log 0.110 over 0.090. And in our other one, we've got pH equals still 5, same pKa value, plus the log of 0.030 over 0.170. Calculator time. So on the left, we've got 5.09 for our new pH. On the right, we've got 4.25 for our new pH. And we want to look at our percent change. So we're going to do, this would be like percent error. 5 minus 5.09 over 5 times 100%. And absolute value 5 minus 4.05. Yeesh. Minus 4.25 over 4.05 times 100%. The mathematically inclined among you may be able to see that, yeah, it's going to be a bigger percent change for the one on the right. So in our equal amounts case, we get a change of 1.8%. In our not equal amounts version, notice that we have a lot more acid. Our HA is a lot higher than our A minus. So even though we have an excess of the acid, which is what's going to be neutralizing the base, we're still seeing a bigger pH change. And that bigger pH change is 0.2 divided by 4.05 times 100. So this is getting a 4.9% change in pH. It's also seeing a larger actual change in pH. We went from 4.05 to 4.25. So we changed by 0.2 pH units. And in our first case, we changed by less than 0.1 pH unit. So even though it might feel like our pH should change less, if we've got an excess of acid and we're adding base, it still ends up changing more. Questions about what we were looking at there? The big takeaway is our buffer is going to be best. It's going to have the biggest ability to buffer out pH change, the smallest pH change when our amounts of acid and conjugate base are equal, or base and conjugate acid are equal. So just this bolded bit, that would be a bit of buffer trivia for you to memorize. To be reasonably effective, we should also have relative concentrations that don't differ by more than a factor of 10. So if we wanted to state that a different way, our ratio of base to acid should be at least 0.1 and no bigger than 10. Base and acid should be within an order of magnitude. Within a factor of 10 of each other. So let's say that we've got 0.10 moles acid. Our limits for the amount of base that we could have to make this a reasonable buffer . 1 mole of base. That would be the high end, the most base that we would want to have in this situation, because that would be 10 times our amount of acid. That would still give us, some effectiveness for our buffer. So no more than 10 or no more than 1 mole. And no less than 0.01 moles base. Because if we go below that amount, that is also going to bring our ratio out of that factor of 10. This isn't to say that you can't have a solution where those are different by more than 10, where you also get some buffering action. It's just not going to be as effective, and so the general rule of thumb is that those should be no different than a factor of 10, closer than a factor of 10 from each other. Our absolute concentrations also make a difference. So we've been looking at the relative numbers, like one compared to the other, but the actual amount that we put in is also important. Our buffer is most effective when the concentrations are high. More acid and conjugate base, still with the same ratio, means more buffer power. Because when we make little changes, if we have a lot of buffer, our relative amounts aren't going to change very much. Whereas if we have little amounts, those changes are going to be relatively larger. And the relative change is what Henderson-Hasselbalch cares about, since we're going to do a ratio. And we'll see that on this next slide. So large absolute amounts minimizes the relative change. when we add acid or base. So we're looking at that same acid that we had before. It's got, this time, equal amounts of acid and conjugate base. All that we've changed is in solution 1, we've got 0.50 moles of each. In solution 2, we've got 0.050 moles of each. Since we have equal amounts of both and the pKa is 5, our initial pH is also 5. So we are starting from pH equals 5. For our first solution, our pH is going to be our pKa plus the log of our conjugate base over the concentration of our weak acid. And on the right, it's the same idea, just different amounts. Okay, so those are the values that we're plugging into the tables. And these are buffering out the same amount of base. So 5 plus log 0.51 over 0.49. In solution 1, our pH jumps up to 5.02. And in solution 2, our pH jumps up to 5.18. Since we had the same starting place of 5, I don't think we need to look at the percentages because we can see that the absolute change in pH was higher, so the percent change is also going to be higher. The ratio of A minus over HA changed less in solution 1. And that's why we saw a smaller pH change as well. For our buffer range, we can calculate the outermost points of the effective pH range of a buffer. This is especially helpful if you're going to be trying to make a buffer solution and you know what pH you want it to be in. This idea will help you select a good weak acid or weak base. So our lowest pH that we can put in is where we have 1/10 of the concentration of our acid compared to our base. So 10 times more base than acid. In our Henderson-Hasselbalch equation, pH is pKa plus log of the base over the acid. If our acid is 1/10 of the concentration of our base, let's set our acid to be 1. then in the Henderson-Hasselbalch equation, it's going to be pKa plus log of 10 over 1. What? No, it would be 1 over 0.1. That also doesn't work. I think the slides are maybe messed up. It doesn't really matter. The takeaway here is this log of, oh, sorry, base equals 0.1. It really is Monday, isn't it? Okay, so we've got 0.1 over 1. So we've got 1/10 the amount of base compared to our acid. So we've got pKa plus log of 10 to the minus 1, or 1/10. The log of 10 to the minus 1 returns a value of -1. So our lowest pH that we would want to see is the pKa minus 1 unit. The upper end is 10 times more base than acid. So a higher concentration of base. So pH equals pKa plus log, we set our acid to be equal to 1. So we're going to have 10 for our concentration of base. So pKa plus log of 10. 10 raised to the what power gives us a value of 10. Solving that logarithm, it's 1. So pH equals pKa plus 1. So this is based on those relative concentration amounts that we saw earlier. I'll go back to it. This slide, right? The base and acid should be within a factor of 10 of each other. So we're looking at the case where we've got 10 times more base than acid. That's going to be our high pH. 10 times more acid than base, that'll be our low pH. And based on our Henderson-Hasselbalch equation, the lowest that we would want to go for our pH is 1 unit below our pKa. The highest we would want to go is 1 unit above our pKa. And that should be here on this next slide. So the takeaway of this, the general rule of thumb, is the effective range is 1 unit of pH on either side of our pKa. The further we stray from that pKa value for our pH, the less effective our buffer solution is going to be. So it's going to be most effective when our pH is equal to our pKa, but will still be reasonably effective plus or minus 1. So if our pKa is 5.73, we can make reasonably strong buffer, reasonably effective buffer, up to 6.73. That's our pH. And as low as or down to 4.73. Just as an example. So if we were trying to do a buffer that was at like 7.4, then whatever this acid is that's got the 5.73, that's not going to be a good weak acid for us to use to make that buffer for 7.4. We would just choose a different weak acid. And to practice those selection methods, which of these acids would you want to combine with its sodium salt to make a solution buffered at 7.35 pH? If you have 500 milliliters of a 0.1 molar solution of the acid, what's the mass of the corresponding sodium salt you need to make the buffer? So the first thing we're answering is, which of these is a suitable weak acid to make this buffer? We have a table of acids and pKa's on the right. So our goal is pH of 7.35. Only one of these acids is suitable to use as a buffer for that pH. Which one is it? Which one?
The last one.
Yeah, it's the last one, the hypochlorous acid. So hypochlorous acid is the one that works here because it's got a pH that's in the same vicinity. It's within 1 pH unit of our target. I think this is formic acid and our nitrous acid and our chlorous acid are not going to work. They're too far away from our pH range that we're looking for of 7.35. So the pKa is within 1 unit of the desired pH. And now the question that we want to ask after we've selected our buffer is, how are we going to actually make the buffer? So we are looking for mass of the corresponding sodium salt. What's our formula going to be for the corresponding sodium salt of HClO? What's our chemical formula? Sodium salt of HClO is another question we could ask ourselves. What's the conjugate base of HClO? ClO minus. So the sodium salt is going to be NaClO. The sodium salt is the sodium version of a salt. How we add conjugate base. So the sodium part of sodium salt, meaning that we've got sodium as our counter ion to our conjugate base, salt just referring to an ionic compound. And we're calculating eventually mass of the sodium salt, so we know how much we're weighing out on our balance to add to our solution. But we need to use an equation to figure out what amount should we have in our solution. And we're going to be using our friend Henderson-Hasselbalch. Conveniently, we've got pH of 7.35 that we're trying to target. So this time we're not solving for pH, we're using pH as one of our inputs. We also have our pKa, we've got that from our table. And we've got 500 milliliters of a 0.10 molar solution of the acid. Underline that one in blue. So plugging in just all the things we've got, 7.35 equals our pKa, 7.54, plus the log of concentration of the base over 0.10 molar. And then we get to solve that for log of A minus, or just A minus rather. Questions so far? So we're going to transform this a little bit. Subtract 7.54 from both sides. We get negative (0.19) equals log concentration of A over 0.10 molar. We can separate out our logs. One of our helpful properties of logs is when you're dividing two things inside of a log, that's the same as subtracting the logs of those individual components. So we'll expand that out. So log of concentration of A minus minus log 0.10. And if we do a little bit of rearrangement, I'm skipping some steps because I'm very much out of room, we get to something equals log A minus. That should be in red. So we get minus 1.19 equals log of A minus. If we do the 10 to the both sides thing, do an anti-log, 10 to the minus 1.19 means our concentration should be 0.0645 ... molar for our conjugate base. We can check if this makes sense. So the check that I am doing in my head to see if this makes sense, we're looking at the pKa, 7.54, the pH, 7.35. Our pH, our target pH, is lower than our pKa. When our concentrations are equal, our pH will be the same as our pKa. If we have more acid, our pH will be lower. If we have more base, our pH will be higher. We got a value of our conjugate base that's less than our concentration of acid, which is 0.1 molar. That means we've got more acid than base, so we would expect our pH to be lower. So this fits with what we might expect. And then to wrap up the problem, to find the mass of the sodium salt, we're taking this molarity 0.0645 ... molar. Our chemical here is sodium hypochlorite. We're going to use our 500 milliliters to convert it into moles. So remembering that molarity is moles over liters, we can multiply by 0.5000 liters to get moles of sodium hypochlorite. And then we can multiply that number by our molar mass. So 35.45 plus 22.99 plus 15.999. Let me calculate that without the thing. So our molar mass should be 74.439-ish grams over moles. I'm doing this real quick because I just assume that you can do it at this point. So 2.40 grams of sodium hypochlorite. And this is like a little bit off because our volume would increase when we add this. It's like not exactly the best way of doing it. We would probably want to make up our buffer fresh, add this in before we get up to our volume, but that's kind of beside the point. Questions about this problem? Basically, what I'm showing you here is we can use the Henderson-Hasselbalch equation to calculate other things in the solution. Like we could also, if we knew our concentrations and we knew the pH of the solution, we could calculate an experimental pKa, but we can also calculate our buffer components as well. And we'll get to buffer capacity next class.